First question here on the alcohol practice worksheet asks us to name these simple alcohols. So of course the first step is to identify the longest chain, and we should always start numbering that chain nearest the hydroxyl group. And so this chain would be numbered 1, 2, 3, 4, 7. And so we have heptane. Heptane turns to heptanol. And that would be 2-heptanol. And then we have to identify the substituents. Don't get confused by this methyl group. It is not a substituent. It is part of the main chain. It is the first carbon of the main chain. Looks like we have 4-ethyl and 6-chloro. So we can write that out in alphabetical order. 6-chloro, 4-ethyl, 2-heptanol. And then we need some stereochemistry designations, S or R. Around carbon number 6, the chlorine is the highest priority, followed by carbon number 5 with all the rest of its carbons attached to it, and carbon number 7. And then the hydrogen, of course, is facing forward. That is the lowest priority. And so if we count upwards, 1, 2, 3, we get a counterclockwise direction. We have to reverse that because the hydrogen is in the wrong position. And so that becomes R. So it's 6R. And that will be... And 4, with this ethyl group, carbon number 5, 3, and this starred carbon are all identical. They're all CH2s. So then we go one further on the chain. Carbon number 2, carbon number 6, or this carbon here. Carbon number 6 takes priority because it is attached to a chlorine, whereas 2 is only attached to O, and this carbon here is only attached to 3 hydrogens. And so highest priority with respect to carbon 4, the stereocenter, is the left branch, then the right branch, then the ethyl group, and then the hydrogen that we can't see but is projecting back into the board, or into the page. And so counting in order, we get another R. So this would be 4R. 4R, 6R, 6-chloro, 4-ethyl, 2-heptanol. This one is much easier. You can observe there are 5 carbons in the chain, so it is 2-pentanol. And then the stereochemistry around this carbon, priority goes to the O, then the larger chain, then the smaller chain, and finally the hydrogen. And so this is counterclockwise, and so this is S, 2-pentanol. We don't need a 2S here because there's only one stereocenter. If you put the 2S, that's fine, but really you don't need the 2 because there's only one stereocenter. Alright, ranking the compounds in terms of acidity. 1 is most acidic, 3 is least acidic. We're going to look for the effect of electron withdrawing groups and or resonance. There's no resonance possibilities for any of these, and so we'll see which one has the closest and most powerful electron withdrawing groups, and that are these chlorines. So those chlorines are the only electron withdrawing groups we see, so that would make this alcohol the most acidic. Then we can look at sterics, and this alcohol is much more sterically hindered, and that decreases the acidity, if you remember. And so we'd expect this one, propanol, to be more acidic than the middle alcohol. So the least acidic is this most sterically hindered. The most acidic is this one that has the, remember that we're discussing really the stability of that O-. And so that O- is more stable when there are electron withdrawing groups attached nearby. If this is more stable, that means that the parent alcohol is more likely to give up its hydrogen, making it more acidic. Here's a couple reactions. We predict the product. This is a generic oxidation reaction. And so really what we're going to do is increase the number of CO bonds. And on this alcohol, the only way to do that is to turn it into a ketone. We have 2 CO bonds now as opposed to 1. We've actually lost 2 hydrogens, this hydrogen and this hydrogen. So we've lost hydrogens, gained CO bonds, and that's the mark of an oxidation. And here we have a sort of a substitution reaction where we're going to exchange this OH for a Br. So we're going to end up with butyl bromide plus water. And if you don't put on the water, that's okay. Most of the time organic chemists don't really care about these inconsequential byproducts. In Gen Chem, of course, we are very concerned with keeping our equations balanced. And so in this case, I should probably have my oxidizing agent somehow talking to two hydrogens, but really we never draw that, so I would leave that off. You're just going to confuse any viewers of your reactions on paper. Okay, so now we're looking at boiling point, the physical properties of alcohols, and we know that boiling point depends on intermolecular forces. The stronger the intermolecular forces, the higher the boiling point. And when we have OH groups, as we do in alcohols, we have the opportunity for hydrogen bonding, which is the strongest intermolecular force. So the more opportunities for hydrogen bonding we have, the higher the boiling point. So this would have the highest boiling point. And I didn't give you a ranking system, so we'll just write highest here and lowest for the other one. And so butane, I hope that you would observe, has no exciting intermolecular forces. It is not polar, it does not have OH groups, does not have NH groups. And so butane would have the lowest boiling point, and this one is in the middle. This one has hydrogen bonding, but not nearly as much as this propylene glycol, this 2-alcohol compound. So here's the mechanism for the reaction of 1-butanol with HBr, and we know that the product should be simply replacing the OH with Br, and the byproduct then is water. And so we want to draw the mechanism for this now so we can get a better understanding of how it works. So we'll fill in the lone pairs on the alcohol, and the lone pairs can be protonated by the hydrogen in the strong acid, and there should be a bond between the H and the Br. We'll pretend that that falls back onto the Br, giving us Br minus. And so we end up with this protonated alcohol here. Oxygen has one lone pair left. That means it gets a plus charge. And as promised, we have the Br minus that has 4 lone pairs around it. And so now we have a good leaving group here. And we can do an SN2 reaction to push off water, forming the neutral H2O. And really that brings us to the product. So here this arrow is showing us water forming. We're getting another lone pair formed on the O. So now we have 2. And the bromine has substituted then for the H2O. So that's an SN2 reaction. So that's the mechanism for the substitution of an alcohol for bromide using HBr. So the nucleophiles in this mechanism are a couple of them. The first one is the alcohol using its lone pairs to attack the hydrogen. The nucleophile is whatever donates lone pairs or electrons to an electrophile. The second nucleophile is this bromine. The bromide anion can use its lone pairs to attack the carbon, kicking off the water molecule. So the bromide and the alcohol are both nucleophiles in this case. Electrophiles will denote with an E+. The first one that we see is the hydrogen. It's being attacked by a lone pair, so it is denoted as an electrophile. And the second electrophile then can be this carbon. It is also attacked by a lone pair on the bromide. And so you see in this case we have nucleophiles attacking electrophiles, nucleophiles attacking electrophiles. You'll never get a separate electrophile sitting around not associated with a different nucleophile. They're always going to be in pairs. Nucleophiles will always react with electrophiles.